So now we're going to talk about traveling waves, waves that move left to right, up and down. And we're going to think about the shapes that we were talking about previously and make them move somehow, mathematically at least make them move. So how do we take a snapshot graph, a picture of a wave, a shape that has a certain shape, and make it travel left to right, up and down as time goes on? We're going to assume that the wave doesn't change its shape at all. And most waves do change shape in reality, so we have to be a little bit more complicated to do things perfectly realistic. But we're going to start off simple and think about a shape that doesn't change. And so if we have a shape at time equals 0, we call the function for that d of x comma 0. The 0 represents time equals 0. So that's some equation for a shape. And then we're going to make it move. And all this involves is making the function shift to the right or to the left. So how do we actually shift a function to the right or to the left? Just mathematically. Just forget about physics. Just think about mathematics. How do we take a function and shift it to the right or to the left? Well, shifting it to the right, all we do is we take x and we replace it by x minus the amount of shift that we want, x minus d. So d is the amount of shift. So here are a couple examples. If I had a sine of x divided by x, that would be this bluish, greenish looking graph. And if I wanted to shift that to the right by 1 meter, or whatever the distance, whatever the units are, all I do is I take x and I replace it with x minus 1. And I do that everywhere I see an x minus 1, x minus 1. And that gives me the orangish looking graph. So it looks like exactly the same thing as what we had before, but it's been shifted to the right. And then here's another example of an exponential, something called a Gaussian. This is e to the minus x squared. And that's this bluish green curve here, centered on 0. If I wanted to shift it to the right, I substitute x. For x, I put in x minus 1. 1 is the amount of the shift to the right. If I wanted to shift to the left, then I would put x plus 1, or x plus 2 if I wanted to shift 2 units to the right, to the left. So the amount of shift, it depends on what you put in here for that distance d, and the direction of the shift depends on whether you put a minus or a plus in there. So shifting to the right, you put a minus. Shifting to the left, you put a plus. So the key then to making a traveling wave is to make that shift a function of time. And so the amount of shift that you're going to have depends on the time as well as the velocity of the wave. So we're going to set that shift, the amount of shift d, equal to the velocity times the time, because that's the distance the wave will have moved in some time t. The faster the wave is moving, in other words, the bigger the speed, the bigger that displacement, that distance is of the shift in that amount of time. So all we do to create a traveling wave is we take our equation for the wave shape at time equals 0. It depends on position x, and we simply replace x with x minus vt. That would give us a wave that travels to the right. So here's a couple graphs in sequence, all just plotted on the same graph. This is that exponential function, e to the minus x squared, at time equals 0. This is then the same graph, the same wave shape, but at a later time of 1 second. And we're assuming the wave has a certain velocity of 2 meters per second. So this is a wave that's traveling to the right with a speed of 2 meters per second. To graph this, to show this motion, all I do is I plot this function at different times with a shift equaling the velocity times the time. And I've just plotted 5 different specific times here to show these graphs. Now, of course, you're not going to see all these plots at one time. These are all different times. So this animation shows more of what you'll see in reality. Right now, we've got a plot of this graph at time equals 0. And if I hit the play button, all it's going to do is it's going to replot the graph at different times. And because of the velocity of 2 meters per second, those graphs are going to be shifted to the right by different distances, 2 meters per second multiplied by each successive time. So there goes the wave, and you can see that it's just a plot at different times. The shift is different for each time. I can speed this up with these little buttons. I can slow it down with this button. I can actually reverse the order of time with this button if you want to. So this is how we create a traveling wave. We just simply take a shape that we want, and it's a function of x, or it could be a function of y, whatever the variable is, whatever the direction is that the wave is moving. And then you change that variable, you substitute for that variable x minus vt or x plus vt, or y minus vt or y plus vt, whatever the direction is that the wave is traveling, that would be your variable x, y, or z. And then you replace that variable with that variable minus v times t or plus v times t. And that's all you have to do. It's very simple. So let's go back to the sinusoidal wave that we had before. Here's our equation for the shape at t equals 0. It's just a sine function with an amplitude. And it has this coefficient in front of x that's kind of like a unit conversion sort of thing. And then we have a phase constant to be, fairly general about what's going on at the origin at x equals 0, at t equals 0. So to turn this into a traveling wave, we simply take x and we put in here x minus vt instead of just x. And now it's going to be a function of time because there's time in the equation. It's not going to be the graph at just t equals 0, although it could be if we plugged in t equals 0. We get the same thing as what we had up here. So we simplify some stuff. We multiply through by the 2 pi. We have a 2 pi times x, and we also have a 2 pi over lambda times x. Then we have a 2 pi over lambda times minus vt, so we have that here. And then we have the plus the phase constant. And then if we remember some things about waves, we have a 2 pi here, and we have a v, and we have divided by lambda. So if we remember this equation that for periodic waves, the velocity is the wavelength times the frequency. And in this equation up here we have v divided by lambda. Well, v divided by lambda is just f, the frequency. F. And remember f is the cycles per second frequency. This is what we call often the linear frequency. So we put that in there. So we have 2 pi over lambda times x minus 2 pi times f times t. And then finally, to save chalk if you're working on a chalkboard, or save ink if you're writing on paper, we take these things 2 pi over lambda and we give it a new name. We just call it k. It's also called the wave number. And we take this 2 pi f and we give it a new name. We call it omega. And it's also called the angular frequency because it has a 2 pi in here and it has a frequency inside of it. So it's an angular frequency. Even though with this wave the medium is moving up and down or left and right depending on what's going on, but nothing's really going around in a circle. But we still use the same word, angular frequency, because it's the same kind of quantity, 2 pi times a linear frequency, that we saw this when we talked about circular motion and simple harmonic motion back in Physics 1. So this is our final equation. For a sinusoidal traveling wave in one dimension, it's traveling in the x direction. So the variable inside of here is telling you what direction the wave is moving. The fact that we have a minus here between the position, the direction and the time, the coordinate x and the time t, that minus means that it's traveling to the right, or it's traveling toward positive x values, which would be to the right. And then we have a phase constant in here. So this is our final equation for a sinusoidal traveling wave, a wave that has a sine shape or cosine shape, and it doesn't change as time goes on, but it moves to the left or to the right. So what you would typically do then is you would choose a wavelength and you would choose a velocity. Once you've chosen a wavelength and a velocity, then you have the frequency, because you can calculate that from the velocity equals lambda times frequency equation. And then you also would have to choose a phase constant. Once you've chosen those three quantities, wavelength, velocity, and phase constant, then you have pretty much everything you need to know about the wave, except, of course, the amplitude. You would have to choose an amplitude as well. So there's really four things in this equation that you can choose: amplitude, wavelength, frequency, velocity or velocity, and then the phase constant. You don't need all those things. You don't need velocity, wavelength, and frequency. They're all related. Okay? You just need two of them, and you can calculate the other. So here's a little animation just showing a wave moving, a sinusoidal wave moving to the right. As I click play, you can see it traveling to the right. The little peak here moves to the right as the wave moves along, and the shape remains the same all the time and everywhere. So that's fairly straightforward. So finally, back to this example that we started last time. If we what we had before was, we said at t equals 0 we have a sinusoidal wave on a string that causes the piece of string positioned at the origin at x equals 0 to have a displacement of minus 0.5 times the amplitude. So that piece of string is halfway down below the equilibrium position, halfway to the maximum displacement below the equilibrium. What is the phase constant? Well, we found that it could be two things. It could be negative pi over 6, or it could be negative 5 pi over 6. Which of these are we going to use? Which one do we want to use? And so we said we need to consider the motion of the wave, really, to figure this out. We kind of talked about this graphically last time, but now we can think about this more mathematically. We have to consider the direction of motion, the motion of the wave itself. So let's go to this more correct equation now that we have, more general equation that incorporates time. And remember that this phase constant is telling us about the position of the point of the medium at x equals 0 at t equals 0. But it isn't necessarily telling us about the motion of that point. So we have to think about velocity. And we're not talking about velocity of the wave necessarily. That's incorporated into this equation because we know the wavelength and the frequency. What we're talking about is the velocity of that point in the medium at x equals 0. So this equation right here gives us the displacement of that point in the medium. So when we talk about velocity of anything, velocity is always a derivative of displacement with respect to time. So if we differentiated this equation, that would give us an equation for the velocity of that piece of the medium as a function of time. And it won't give us an equation for the velocity of the wave. That velocity is just a number that's incorporated into the wavelength and frequency. It's related to wavelength and frequency. But taking a derivative of this displacement equation, this is the displacement of the medium, that derivative gives us the velocity of the medium. And so here's the velocity. Take a derivative of the displacement equation. The sine function turns into a cosine function, positive cosine. And when we differentiate with respect to time, everything inside of the sine function, just an omega comes out. And that comes out in front here. I forgot to mention that we're just going to do this with a plus in here. You might say, well, there's a plus there. That looks different from before. Let's just assume the wave is moving to the left, just as an example. It doesn't have to be, but suppose it is moving to the left. The wave is moving to the left. So we'd have a plus in here. And so that brings out a plus omega. If we had a minus in here, we'd have a wave traveling to the right. That would bring out a minus omega when we take this derivative. So this is our equation for the velocity of the medium as the wave is traveling by. So we could plug in a particular coordinate, a particular position for the medium, and we could plug in a particular time, and we could calculate what the velocity is of that piece of the medium at this moment in time and at that position in space. And it depends on our phase constant, of course. We'd have to plug in the phase constant. So let's look at the origin. The point 0, 0, position equals 0 and time equals 0. At that position and at that time, this is what the equation becomes. A times omega, the amplitude and times the frequency, times cosine of the phase constant. And so if we plug in the two phase constants that we have, negative pi over 6 and negative 5 pi over 6, these are the two results we get. Square root of 3 over 2 a times omega, and negative square root of 3 over 2 a times omega. And a and omega are always positive numbers. That's just what they are. They're always positive numbers. And so if I had a phase constant of minus pi over 6, this would mean that at this point in space and at this moment in time, that point is moving upward and has a positive velocity. It's a positive number. If I had a phase constant of minus 5 pi over 6, then the velocity is negative. That point in the medium is moving downward. So to choose which phase constant is correct, you not only have to know where the piece of medium is at the origin. Is it above equilibrium? Is it below equilibrium? You know exactly what is the displacement of that point at x equals 0 and at time equals 0. But you also have to know what is it doing. Is it moving upward? Is it moving downward? And you of course also have to know what the wave direction is. So you have to have the right equation here, plus omega or minus omega t. So once you know those things, you can determine which phase constant is the correct one to use. So in our case, if we knew that the medium was moving, that point was moving upward, if we were told that, if we were given that information, then we would know we'd have to use the minus pi over 6 as our phase constant. So finally, this little figure gives us a bigger picture of what's going on with the medium. This is a snapshot graph of a wave on a string, for example. And let's suppose the wave is moving to the right. All these points are moving in different ways on the medium itself. This is the string. This blue line is the actual string, and these black dots are various points of the string. At this moment in time, the medium is moving in very different ways at different places. In some places, the medium is moving upward with a high velocity. In other places, the medium isn't moving at all at that moment. the velocity is 0. And sometimes, this piece of medium, as time goes on, eventually it's going to move downward. And eventually these other points, they're moving upward. They're eventually going to stop and come back down. So the velocity of the medium is very different from the velocity of the wave. And the velocity of the medium is given by that derivative equation, the derivative of the displacement. So the velocity of the wave is some number, but the medium itself is vibrating up and down. At least for a transverse wave, the medium is moving up and down perpendicular to the motion of the wave. And the velocity of the medium varies from having 0 velocity when the displacement's maximum to having a high velocity when the displacement is 0. And it just continually changes over and over again as time goes on. So that wraps up just the idea of traveling waves, but we talk specifically about sinusoidal waves. But the idea is that you can have any wave shape. There can be all kinds of crazy wave shapes. And if you want to describe a traveling wave that has a shape that doesn't change, all you do is you take that function for that shape and you put in there, you stick in, instead of the position x, for example, you put in x minus vt or x plus vt. And that'll give you a mathematical shape, a mathematical wave that travels to the right or to the left, that maintains its shape. If you wanted to have a shape that does change, then you can multiply things. You can multiply the function by, like, functions of just time, for example, so that as time goes on, there's some function that causes the shape of the wave to change. It gets a little more complicated, but we won't have to worry too much about that in this class. So that's all for this lecture. The next one we'll talk about is we're going to think more in 2 dimensions and 3 dimensions and think about waves in multiple dimensions. And to do that, we have to think about more than one coordinate. Instead of x, we have to have x and y, or x, y, and z, for example. So that's what we'll do next.